storage based on Delta Lake to save like process data, different features. Then there is there are ML sandboxes that are based on Databricks, the outputs like Python scripts and Docker files and whatever is needed to, whatever artifacts are needed to serve this flow or submitted in the CI process in Azure DevOps and then integrated with basically runtime for either real-time serving or for batch serving. And experiments were tracked in MLflow, and models were also stored in MLflow as a model registry. So what were like the typical limitations of that this team were facing? So at a high level, there were basically pros and cons of these solutions, of this approach. Actually, like the biggest advantages were that this approach actually provided high flexibility in the sense that each team used to build whatever they want, support their own like features from the platform perspective. There were very limited dependencies across the team. They used to build it pretty much independently, and it was relatively easy to like manage it from organizational standpoint because all domains were pretty much independent. But there were a number of disadvantages, as we talked in the beginning, predominantly related to limited functionality and high cost of ownerships across these platforms. And there were like a number of typical technology gaps in each of these solutions. For example, from data management perspective, typically they did not have any tools for data quality control, for data governance. Also, like most of the teams, they tend to create very large processing graphs and with like many different data engineering and model training steps, which was also very challenging to manage. From the infrastructure perspective, they of course lacked of like infrastructure as a code, automation. Some steps were like implemented in semi-manual way. From the production serving perspective, again, in many cases, they just, in these teams, they just used to build some artifacts and deploy them in production and in semi-manual mode with some manual tests, configuring monitoring in a manual way. And of course, functionality from the MLOps perspective was typically limited in the sense that they, in many cases, did not have proper experiments tracking, no feature stores, no A/B testing frameworks, and so on. And in this situation, basically, there were like three strategies that were considered as a potential next step forward. So basically what we just discussed, I would call it like decentralized approach, meaning that there are like multiple different teams, each of which has specific goals that they are pursuing, and they are free to use whatever technology tools for achieving these goals. And this way they typically can be like very motivated because they have no external dependencies. They completely own the solution that they develop. The second approach is to build a centralized platform, like a corporate ML platform that serves all the teams and serves all the needs. And basically, it enables different domain teams to onboard their use cases, develop their use cases, having very limited knowledge and almost no MLOps, DevOps resources. But development of such a platform, it's like in some cases it's a good idea, but in many cases it like represent a lot of challenges. For example, if you think about this particular case, they had like 30 different teams, and each of these teams was a kind of unique in terms of how they, what kind of use cases they built and how they approached them, and basically building a platform that would cover all these needs, all the required capabilities would be very time-consuming, very challenging. But the third approach that was considered here was actually something in between of these two extremes. It was building an MLOps center of excellence. Basically, the idea was that it will be one centralized team for creation of essentially like templates and reusable artifacts that can be then customized for each specific team. And then it will be like a standardized process for creating basically instances of ML platforms for these different teams based on these centrally managed templates. And but at the same time, these platforms could be customized for the needs of each individual team, so that on the one hand, we would have many different, like each team will have its own platform in a sense, but the platforms will be created according to best practices and standards that will be centrally managed by a team that specializes in basically building ML platforms according to best practices. So from the technical perspective, how it was implemented, how the solution was envisioned. So basically the vision was that the COE team, Cloud of Excellence team, will create standard templates that typically will involve basically two sets of artifacts. First set of artifacts are related to infrastructure as a code scripts for the platform itself, and then templates for different types of top-light projects, like projects for batch processing, stream processing, real-time serving, and so on. And then for each particular domain team or for each particular project, they will basically take these templates, do customizations according to the needs of individual teams, create workspaces or environments, and then the domain team will use these repositories, in particular these project repositories, to create the pipelines or whatever artifacts they need to create, and then these artifacts will be deployed in production using the capabilities of this platform created out of the template. And also, it's important that this solution was envisioned as a multi-cloud solution. So at least, for beginning, like Azure and GCP was supported. So basically, there was a need to provide this this flexibility as well as ability to customize the capabilities of the platform for individual teams. So in this approach, of course, one of the central questions is how exactly these templates are managed, because it's not a trivial process of how to organize this so that the platforms can actually be updated. And at a high level, the workflow was essentially as follows. Basically, the workflow that was implemented is that it starts with the data science team, like the main team that needs to create an instance of a platform for a specific need or specific use case, and they specify. They select one of the project types, they select ML services that need to be provided by the platform, and then they essentially create like a service request for COE team, and then the COE team, they take appropriate template and create a repository that contains all infrastructure as a code artifacts for this new project. And then for new projects, they basically do customizations of these templates to meet needs of a specific team. Then they essentially recreate the environments, essentially performing like Terraform apply, and then they create a repository for the actual projects repository. There are the actual data engineering scripts or data engineering jobs or model training, model serving scripts will live. And it also can be an update of an existing project, so that in some cases, these data science teams, they can create requests to customize or update or improve the existing project. And in that case, it is again handled by the COE team, so that they do customization of the existing project, of the existing template, and then basically recreate the environment. So in this later case, how these updates are handled, also another important aspect of it is that basically the goal was to reduce the load on the COE team, so that they do not handle all possible requests, all possible updates that needs to be done in the company. And to enable that, the approach was to basically create like several different types of several different like tiers of updates, and so that some updates can be handled by essentially like data science teams, data scientists themselves. Some updates can be handled by DevOps engineers, so MLOps engineers in each individual team, and some updates can be handled by the COE team. So from that perspective, typically how it worked. Updates in the modeling logic, updates in configurations were usually handled by like data scientists themselves, and they were provided with tools for making these updates and then deploying these updates to production. The updates that require to change the environment itself, for example, types of instances, amount of resources for production serving and so on, were handled typically by MLOps engineers at the domain level, and more complex updates were usually required to involve the COE team to handle. And in this later case, typically the approach was that domain teams, they, like in most cases, domain teams, they used to create requests themselves, so that they, in general, they were familiar, of course, with how these platforms are like instantiated and familiar with the deployment automation they used to create. The requests themselves, then these essentially pull requests used to go to the COE team. They used to they used to review these updates, make changes if needed, merge these pull requests, and then apply updates to the actual environment. So this way it was basically the collaboration between the domain teams and COE teams in a productive way, so that the workload on the COE teams was relatively limited. So now let me talk about the migration strategy, how the whole program was structured, because it also has like certain implications on the design of the solution. So basically, the entire program was structured in a way that basically the goal was to enable like step-by-step migration, and also migration in such a way that multiple, this like 30 different teams can perform this migration in parallel, so that the entire migration time frame is reasonable. And from that perspective, basically, the process started with creation of these common templates that we just talked about, and after that, for most teams, the actual migration started with migration of this of the serving layer, which is shown in green here, because, like in most cases, at least in this, like in this particular case, serving layers were relatively lightweight. They pretty much were like deployments of model runtimes for like real-time scoring, and it was relatively easy to migrate them as a separate step. And at the same time, data engineering processes, model training processes were remained basically on the legacy platform. But then the next step was to onboard the basic data sets to the newly instantiated platforms, migrate data engineering processes, then migrate, design and like implement new ML pipelines for modeling, training, and batch inference, and then roll out it to production. And then typically this was like iterative process for upscaling to like new markets and so on after that. So to illustrate that, this is an example of how this like intermediate state looked like for one of the projects. So basically, this is the state that like on the left-hand side, there is like essentially a legacy solution for, in this particular case, for producing essentially demand forecast based on like historical sales data and so on, like typical scenario. And then on the right-hand side, there is like a new serving layer that in this particular case was implemented in GCP. So basically, it used to ingest these like forecasted values that were produced in like in the batch mode on a regular basis, and then there was like transactional storage for serving this data to like applications that needed to query these applications in real time. There was the corresponding a corresponding service and a number of endpoints to which legacy applications were connected. And there were also, in this particular case, the flow for serving like asynchronous requests for doing some stock optimization computations. And basically, like this right-hand side part was migrated first, and it was replaced. It replaced the legacy application in a transparent way that did not require to modify this legacy applications. Now let's go a little bit deeper into what specifically was in these different templates, because we talked about this process of like template management and how we do migration, but we did not talk. I did not talk a lot about what specifically what was inside of these templates and what kind of basically capabilities, standard capabilities were implemented. So in one of the previous slides, we talked about the limitations that most of the teams had across these different categories, such as data management, infrastructure management, production serving. And basically, the goal of the COE team was to create standard templates that used to address these limitations. For example, from the data management standpoint, the goal was to enable basically more like data mesh type of a solution, so that different teams can produce data products, and there are standard services for data observability, for controlling the quality of the produced data products, and so on. Of course, from infrastructure management and CI/CD standpoint, the goal was to improve the level of automation. And also was a goal to introduce like more specialized services, for example, feature stores for real-time scenarios, experiment tracking tools, and so on. So how it was implemented? Let's start with the data layer. So this is like a somewhat simplified example of how the data layer was implemented in these templates. So basically, like it included actually like 4 different parts. The first part was basically the development environment. So it included processes for like services for data engineering and data governance. In this particular case, it was implemented on the Databricks stack, and basically the outputs of these processes were data, like for example, engineered features that can be used for model inference purposes. And this prepared data were used in the development environment. The actual models were like deployed in the staging mode. I will talk about how exactly it used to happen in the next slide. Then the second part, of course, was the production environment. So in the production environment, basically the feature store was used for accessing different features using point requests, like in real time. And there was a separate process basically for replicating data from this offline storage to this feature store as a part of the data management, standard data management template. Then from the runtime, data was sent to the collected data, for example, interaction data or feedback data used to send into data streams, and there was a separate like real-time feature engineering pipeline that used to consume this data and apply like the same data preparation, data transformation processes to produce or update the features that can be used to catch up with ongoing data. And the data quality was controlled using Apache Soda framework, and the data was then eventually landed into this storage. And finally, the fourth component was continuous learning pipeline, so that data that this like continuously updated data were used to retrain models that were deployed in production. So then from the CI/CD perspective, which is a counterpart of the previous slide, we also had the development environment. There are in this environment, basically like the actual model training scripts were created, and then it was integrated with CI processes that used to basically create like final artifacts, provision environment for model like model retraining, model testing, and then models were packaged and deployed into ML flow. And then from ML flow, we had deployments, of course, into the development environment as well as in production environment. There are also were some additional components related to observability and model monitoring. And finally, the continuous learning pipeline, it was like basically an instance of this model training pipeline that used to, on a scheduled basis or on a real time, to catch up with latest data updates, and then the produce new model versions that were deployed into the registry and then to production environment. So this is basically, this I hope gives some idea of how like the actual services were implemented and what basically most teams got out of this migration and out of these templates. And there were some additional services. I will skip it for the sake of time. For example, services related to experimentation, experiment management, which is actually a very complex topic by itself. But finally, I just want to mention that this like template-based approach, it can be, this is actually just one possible application of these templates. We can use this strategy to create this cloud center of excellence and instantiate many different models for different teams, but actually the same technique can be used for solving quite different problems. One typical example is building, basically scaling the processes by markets. For example, if you have many different markets globally and you have some process that or some model that needs to work, like initially developed for one of the markets, then basically what can be done is the solution can be templatized so that like typical steps implemented in this solution, like feature engineering, models themselves, business logic on top of it, validation criteria, and so on, can be basically packaged as a generic template and then instantiated for more markets. Yep, so that's pretty much it. Just to summarize, in this talk we spoke about basically how to identify a right problem to solve. As we just talked, it can be a scalability problem in terms of number of teams, but it can also be some other type of problems like managing multiple markets. Then usually it's a good idea to consider different approaches for building the platform. We talked about the decentralized, centralized, and COE approaches. Then we talked about how to design actual DataOps and MLOps services and processes, how to structure the migration by phases, and then how like the future, like ongoing scaling across different markets or development of new additional services can be structured. Yep, so that's it. Thank you.
We have 5 minutes for questions.
Hi, Ilya. Great talk. And I like that it highlights the complexity of this kind of projects. Did you have KPIs that the business had as of the performance of the teams, like before and after the migration? So sometimes like you need to have these metrics that you track, like time to deployment or others. Like what was the rationale behind this?
Mm-hmm. Yep, so there were like a number of, I would not say KPIs, but there were like a number of like specific targets that they were going to solve. Like one of them was actually basically simple onboarding process, for example. And obviously, even if you do not define a KPI for it, it's quite obvious that this approach, like onboarding, it can be done in a matter of days as opposed to, weeks or months with this decentralized approach. Yep, and the second target actually in this particular case was like harmonization of the skill sets, because if you have like this many different teams that like solve their problems in different ways using different technology stacks, then it's difficult from like resource management perspective, how you hire people, how you move people around across different teams, and this approach it basically it obviously provided like improvements from that perspective.
I had a question about the Terraform templates. Did those already exist at the company where you were performing this transformation? Or if not, like how much time was allocated to building those templatized infrastructure models?
Mm-hmm. Yep, thank you. In this case study, these Terraform scripts, they did not exist, but these scripts were created based on the SDKs that are typically provided by cloud vendors. For example, like Google, they provide SDK specifically for like Terraform SDK specifically for their services and so on. So basically, like most of the work here was essentially about taking this like SDKs, doing some extensions for like non-standard things or some things that were like missed by some reason in this SDKs, and then combining all the things together so that these templates can be like actually instantiated in a particular company.
Hey, really good talk. Thank you. So you mentioned about migrating the platform and starting to deliver value from it. So I'm just kind of interested in, you mentioned you started with the model inference because it's relatively lightweight and easier to start with. How did you start to deliver value from things like the feature store and the Terraform templates, which only start to deliver value once other things can use them, if that makes sense?
So just let me make sure I understand your question. So basically, the question is about adding more services and how to get value out of it.
So what your migration strategy was so that you made sure you could demonstrate that you were adding value from these more complex pieces, such as the feature store?
Well, actually, like migration strategy, it was a little bit like more sophisticated than I just shown, because there were some additional goals. For example, there was a goal to redesign the data engineering flows. As I mentioned in one of the slides, basically there were a lot of like issues and challenges related to like complex legacy processes that were difficult to maintain and so on. So as this migration was implemented, like one of the benefits that was gained through it is that these processes were redesigned. That was not just like lift and shift migration, and this way there were simplifications like in terms of management and maintenance of these flows. For example, because we start with migration of this solving layer, we kind of separating it out, then we basically redesign, let's say, data ingestion, data onboarding processes. It's like you can view it as a separate benefit, right? That it's now like a separate process that can be managed separately, and it also can be optimized in terms of resource usage, in terms of SLAs, and so on. Then you move model training, let's say, processes or model inference processes, and this way, basically, to answer your question, basically in each of these steps, you can demonstrate the benefit in terms of like at least from operational standpoint, as well as from like functional improvements. Because in like in many cases, like actual for example, models were improved, and their performance in terms of like business outcomes, like conversion rates or forecasting accuracies or whatever it is, were also improved. If it answers your question.
That's all the time we have for questions, but please join me in giving a round of applause for Ilya.
Thank you.